always interested in what you have to say, and you work for the phenotyping facilities. AgAlumni has funded a lot of those, and so anyway, I'll let you take it away, and we thank you again. And we have some others that are coming up here too. We'll be introducing Lori Hoagland. Next week we have one also, and you can see that there are 4 more for the rest of the season here. So thank you.
Sure. Thank you for the brief but warm introduction. And thank you everyone for coming in person and also online. I appreciate to have this opportunity for me to share a little more in-depth information about the controlled environment and also in-field phenotyping facilities that the Plant Science Institute team has managed and operated to provide service across the College of Agriculture and also in essence across the campus. At this point of time, I'd like to share my screen of my slides. Is that okay? Just now, is it showing up online? Can you see me? Okay, good. So again, the topic of my talk today is the Purdue University's controlled environment and field-based phenotyping facility. I want to provide a little qualifier for this topic. When they asked me, Jan, what do you want to talk? I was like, let me talk about our facilities. But in essence, there are so many great facilities related to phenotyping for plant sensing in the last, I would say, many years developed. So there's no way I'm able to summarize and also introduce all of them, all those great achievements in this 1 hour period of time. So rather, I want to just focus on the 2 facilities that managed and operated by the Institute for Plant Science. So in the year 2013, the Institute for Plant Science was initiated by the College of Agriculture in the Plant Move initiative that was announced by President Mitch Daniel. Since the year 2014, more than $20 million have been then invested into plant science research, plant science education, and those research related to digital agriculture, as well as encouraging entrepreneurship. As part of those great achievement and investment, the college has built 2 phenotyping facilities, one in the controlled environment, one in field. So today I'm going to first lead you through some key capabilities and key capacities in the AgAlumni seed phenotyping facility. After showing the capability and capacity, I'll share with you a few examples of our professors who have carried their research leveraging the sensing capabilities inside the AAPF. Then I'll switch gear to lead you to Indiana Corn and Soybean Innovation Center, which is our field-based phenotyping facility. I'll then introduce to you the UAV-based remote sensing service that our team provides to our customers at Acre and actually, for that matter, in other sites. And also the data pipeline that's related to the remote sensing service. Last but not least, I'll touch briefly on the Plant Science 2.0, the next Purdue move, what we can expect to see in terms of the facility that's coming in the next few years. So the AgAlumni seed phenotyping facility was built in the year 2018. Ever since it was built, the effort in terms of expanding its sensing capabilities and plant holding capacities has never stopped, with the solid support from both the college, the university, as well as industry. Actually, AgAlumni has been a very strong support for us to improve our capabilities and capacities in our facility. So nowadays, if you come to visit us, you can visit us. Actually, I have the virtual link here just for a virtual tour. Or if you would like to have visit in person, you'll realize that AAPF, in fact, is the largest growth chamber-based phenotyping facility in North America. For that matter, we all have challenge to even identify another similar facility across the world for the capabilities and capacities that we possess in the AAPF. So why do I say that? Because with the 2 large growth chambers we have in AAPF, we can hold up to 620 plants that can grow up to 4 meters in height. 4 meters in height because this facility was built mostly by European vendors. Translate into feet that we are familiar to, that's about 14 feet-ish. We have those growth chambers providing very precise and consistent controls over environmental factors such as temperature, humidity of the air, the CO2 levels, the light photo period, light intensity, and what have you. And of course, in terms of we're talking about phenotyping facility, we have to have sensing capabilities. The major sensing capabilities in AAPF consist of 3 digital data acquisition and processing pipelines in the name of RGB, which in essence is the visible band imaging system, the hyperspectral imaging system, and X-ray CT. That's dedicated for the root. Again, I have the virtual tour link at the bottom. If you're interested, you're welcome to visit us online. Or if you have the chance to visit us, you're more than welcome to drop by and we can show you around the facility. Before you go in the virtual reality to visit us, I can show you a quick picture about what you will see inside the growth chamber. You'll see that we have every part sitting on what we dubbed as the automated conveyor belts. In this example, we see the corn plants, the seedlings growing on the conveyor belts. Whenever they need to be imaged or measured in that sense, we'll call the automation system to bring the plant into one of the 3 imaging systems I just mentioned in the previous introduction. So when we image our plants in the visible band, we leverage the RGB or the visible band imaging booth. This imaging booth is very high throughput. It can image up to 120 plants in an hour. The size of the plants is pretty wide. We can image a plant as small as short, about 5 inches in height, up to, again, 14 feet. So it's a very wide spectrum that we can provide the imaging. That covers a lot of different crops. On this page, I list soybean, tomato, kale, basil, wheat, corn. We also have provide support for research in switchgrass and other projects in garlic, and of course rice. So a very wide variety of different crops can be grown in our growth chamber and also imaged by our system. This imaging system doesn't only taking images, it also calculates a lot of information-rich traits such as the size, the width, the height, general morphological information, as well as the color information that can be leveraged in terms of quantifying the growth or the plant reaction to different environments. The good part for this sense system is that it's quick, it's high throughput. We can image a lot of plants in a short period of time. For those 600 plants, we can image them a little over 5 hours. That's the advantage. And also the information is pretty solid with the morphological and size information there. However, there are many information that out of the visible band that this sensor cannot pick up. But those information can be very critical and very sensitive to the status that we want to research on a plant. So there we come with another technology in the name of hyperspectral. Hyper means many. Instead of only looking at the color image, we provide this technology to look for the information or acquire information in the what we call it visible to near infrared band. That's the veneer. Or if we need to go even further, longer wavelengths, we call it short wave infrared. That's the Douglas sphere. So in the hyperspectral imaging system, we have in AAPF, we have both the top view and side view imaging capabilities in both the sphere and the veneer bands. On this screen to the left-hand side, this is a typical spectrum of a green vegetation. We can see there's a short, there's a small bump here in what we call it the green band. And there's a dip here to the right-hand side, and then there's a dip to the left-hand side of this small bump. Actually here, normally people double as red or deep red, and then the blue is to the other side. The reason for this is because chlorophyll absorbs very strongly in the visible band, in the R and G and the B. However, it doesn't absorb as strongly as it does in green, in red and blue rather than in green. So that's why we see there's a small bump in the green band. When you go into the longer wavelengths, beyond 790 to 1000, you realize we have a lot of energy reflected back by the green vegetation target. That's because the pigment doesn't absorb as much of energy in this band. So that's why we see this very typical. That's why it's typical, very typical for green vegetation. Go further into a longer wavelengths. We'll see we switch to the right-hand side of the spectrum. We see there's very typical drops in the reflectance. This is caused by the absorption of light energy by water. So again, this is a very information-rich band in which we can relate the information to the physiological status of the plant very conveniently. So for the facilities capability-wise, if the research needs the information from the near, we can provide. For if it's only from sphere, yes, there's the capability we can leverage from this facility. If the research happens to need the full spectrum information, then our system is able to provide the full spectrum at the bottom and actually connect and overlap the information from both the near and sphere cameras together. Of course, because it's imaging and then because it's spectrum information, then the data can be quote unquote a little messy because we have two-dimensional size and shape as well as the z dimension in terms of the spectrum, right? So normally we double as the data cube. Many times for a end user, even though it's very rich information, it is also kind of like challenging to even visualize or understand how do I even dig into the data that I have. To accommodate our customer to, in terms of analyzing and visualizing that data, our pipeline provides a set of what we double as vegetation indices, which are developed by combining different wavelengths together as an easier way, if you may, to dig into the information provided by spectral information. And also we have the heat maps of different VIs, just so we can help and enable the visualization of our data, just so we can look deeper into what can be done or what can be analyzed in the pixel level. The heat maps to the right-hand side, just an example of the NDVI, the so-called normalized difference vegetation index, a very mainstream VI actually being used in a very wide type of research. This is just an example of different crops in terms of NDVI that we can help the customer to visualize that data. Why is it down here? The third pipeline we have here in AAPF is the CT X-ray system. On the screen here, to the left-hand side, the metal gate here, that's our X-ray source. Once the gate opens, the radiation will go through the target plant, and then the signal detector in the big blue box will take the information. That's the detector. So I'll show this. How do I run this thing? I'm trying to run a video, I cannot. I think because I have a pointer, I cannot run the.
I think you need to change it up the plan.
Really quick laser game.
No.
You click the pen one more time, I think that might exit out.
Sorry?
Click pen one more time.
Pen one more time. Yeah. Right. So thank you. So the concept here is that we need to take multiple shots of this part, just so a two-dimensional image, just so the computer algorithm is able to construct the three-dimensional route. So by running this cartoon actually simulation, I'm just using this example to showcasing actually this is how the system works, in the sense that the plant rotates while the camera takes the shot piece by one frame by after another. Eventually, the algorithm put the three-dimensional data together and segmented out the roots from the soil. Actually, to be honest, this root here, we see this is not simulation. This is the very first one. Actually, this facility applied using that X-ray machine, and our partners in AgCalm create this three-dimensional digital twin for us to demonstrate the capability of this facility. So by combining this root scanning capability, then you have the in essence capability to non-destructively measure the root for multiple times of the same plant. And all of a sudden, it opens the gate for any scientist that's interested to understand the dynamic relationship between the shoot and the root. Or if you are interested in understanding how the root reacts to different environmental conditions, this machine is perfect in the sense of we are doing a non-destructive measurement for the same root multiple times. So the number of reps you will need for your student to go through, to dig out and wash them out will be much less, because then the throughput is much higher. For each plant, if the pot is above 200 millimeters in height, we can scan root in 7 minutes. A deeper pot that's 400 millimeters takes about 14 minutes. It's still short, still slower than the shoot imaging, but in terms of the root study, this is pretty high throughput, I would say. So again, combining the shoot imaging, as I just mentioned, and this capability provided by the X-ray CT, this facility provides a very unique capability for us to understand and measure the same plant, the whole plant, on shoot part and root part simultaneously across a long period of time. So the phenotyping research can be greatly enhanced. Of course, there's a lot of questions I did have the chance to hear is that I don't do phenotype. My research is in soil science. My research is in plant pathology. Actually, think about phenotyping as plant measurement. In many cases, we need to measure the plant manually, right? The different traits, different aspects of those plants. This technology, in essence, provides us the capability to measure plants in different ways for different purposes. Next, I just share with you a few examples as our professors leveraging this capability for a very diverse patent portfolio of their research. Dr. Mosa Mohammed from AgAlumni department, he was one of our early adopters in the facility. He leveraged heavily the growth chamber as well as the RGB imaging system to quantify the growth of wheat plants, the wheat of different varieties. And also he did go one step further to understand how do you quantify the plant reaction of different variety to drought stress. In his research, he published this paper. He mostly leveraged the color imaging system, used the science that's acquired by our color imaging system, and also the color itself, actually, to understand how different varieties would behave and perform differently. That's a unique angle to improve or enhance his research in wheat breeding, actually, for that matter. On the hyperspectral end, Dr. Lori Hoagland from the Department of Horticulture leveraged our visible and near-infrared band hyperspectral imaging system to look into her research to detect cadmium stress or contamination in Kale and Basil. Actually, early on, we see the announcement for Dr. Lori Hoagland to do her presentation later in November. So I'm trying not to steal her thunder here. So consider this as a kind of like a trailer piece. So suffice to say, Dr. Hoagland's lab was able to leverage the sensing capability in AAPF to identify vegetation indices that they can use in detecting cadmium stress in Kale and Basil. And also using the pipelines we provided her, they were able to identify the key wavelengths in the spectrum that are very sensitive or useful for their quantification of cadmium in the model plants in Kale and Basil. For the full spectral study, Dr. Dan Wong actually leveraged the full spectrum capability in AAPF to try to quantify the rise reaction or detect the difference in rise reaction to nitrogen treatment. With high or low nitrogen regime, Dr. Wong, of course, has a much bigger program in terms of trying to quantify the physiological status. A key, small yet key piece of that research is to say, hey, how do we use the hyperspectral information to classify the difference between the rise when they are treated with different nitrogen regimes? Similarly, as the data set for Dr. Hoagland, we were able to help their group to identify key wavelengths that make sense for their identification of different regimes in terms of nitrogen treatment. Using this data, you go one step further to weed out the autocorrelation between the wavelengths because there are a lot of them. So there's bound to be some linear correlation there. So people, Dr. Wong's group was able to separate those two groups very, very easily using this information collected by the hyperspectral sensor. So this is another example of just me sharing with you that think about phenotyping at a wider and a more diverse way of plant measurement instead of just saying I'm a breeder, and if I'm not a breeder, I'm not doing phenotyping. That's not the thing. Actually, this technology can be used in so many different ways for so many different types of research. Let me switch gear to talk about the root again, because root is what some saying this is more than 50% of the story, right? Sometimes it's because it's very hard for us to have the quantitative data from root just so because it's not easy for us to even observe. So when we have the X-ray machine, then first we take a stack of data. In this case, for this machine, we take anywhere from 1,200 to 2,400 two-dimensional images. And then the software package in the name of root force, which is provided by the X-ray machine vendor, then takes over those two-dimensional images, put them into a three-dimensional data set. From there on, the segmentation process kicks in. Then we can basically digitally take out the root from the pot media or from the soil. It's a process so far semi-automated. In other words, a expert has to go in there to identify and create a set of parameters with the appropriate values. Those parameters then is taken over by the software. Then it takes to identify roots that fit within those ranges. So you can see here, this more like fine tuning. This once it's tuned though for each plant, it takes about 30 minutes, sometimes longer. But the tuning takes time. So here I hope I have some engineers in my audience. We can really use your help to look for a more robust way to do the root segmentation in a more robust, more automated way. Of course, after segmentation, then you can have the three-dimensional data, which is very fancy. Actually, up to this point, the facility is able to scan and provide images on quite a set of different crops and plants. On this screen, I list corn to the left-hand side and tomato and soybean to the right-hand side. In the middle, though, I do want to stress that it's not only for the row crops. We can also do trees. As far as the root, there's a way we can help you to look into the shape, the size, and the trait of different crops. And of course, having this good-looking images is already a very unique capability that Purdue's facility can provide. you will be hard stressed again to find even a few other facilities that possess this capability to provide you this type of data to enable the research. However, the excitement probably will wait away in a few seconds. You will ask me, so Yang, so what's the deal? I have this fancy looking corn root. How do I use it? How do I use it to quantify the characteristic of the root or the trait of the root? That's what we dub as trait extraction. Lucky for us, we have collaborated with Dr. Anjali and her postdoc, Dr. Valerie Merlin, in the last few years. As a research group, Dr. Anjali's group has dedicated their time into figuring out how we can extract digitized information from those segmented out root from the X-ray machine. So Valerie takes on the methodology in the way of a skeleton of the root. And after he creates a skeleton of the root, he then has a set of algorithms to go through in which he can create a set of root traits that can help us to quantitatively describe the root instead of just looking at a good-looking image. In essence, his algorithm provides a large set of root traits in the name of total root length, root density. I will not read through them, we can read. But suffice to say, this is a pretty nice data set that we can provide from the facility to facilitate the quantification of root traits. Just a few examples of those traits we're looking here. So if we are comparing the two roots on this screen, the one to the right-hand side looks bigger and more dense, right? But how do you quantify the difference? With the traits, with the array of traits Dr. Merlin provides, we know that the total length of the one to the right-hand side is longer than the one to the left. And the depth and also basically the root in this case of the same age, it digs deeper right one than it is than the one did to the left. And also, if you count the tips of the root, the root to the left, right-hand side has more tips, or you basically so you have more root, you create more root than the one to the left did. And also, we have a way to quantify the root distribution density according to the depth at 25 quantile, 50% quantile, 75% quantile. So there's a lot of ways now that we have this matrix of the root traits to digitally, quantitatively describe a difference or no difference in that sense of a different root or of the same root at different age. Another way to look at the root, breeders always say the roots always be deeper, quicker, and cheaper, right? More energy, more biomass into a deeper portfolio to surgical nutrient of water. Is that really the case? Of course, there's a lot of debate at the end of publication at the end. But how do you quantify what's the size and the crown angle of the different varieties? In the matrix Dr. Merlin creates, he creates what they call it the crown distance. In this case, actually, is the diameter of the crown root. And then if you have the crown root, if you define, say, okay, this is the max diameter of the root, in this case is here, then but which distance from the top of the soil does the root need to take to reach this diameter? So basically, then you have a way to quantify the crown root angle, right? In this case, we can visually on this page visually see there's difference between the root on top and the root at bottom. But our quantitative description, the trait extracted is pipeline that tells you that for the plants at the top, it takes the root up to 230 millimeters. You need to dig up to 230 millimeters into the soil to find the root that's reach 77 millimeter. For the one at the bottom, you only dig to 186 millimeter, which means the root come to that diameter quicker, right? So that's a really much faster way for us to quantify the difference in the root architecture, which is critical for a lot of different reasons. Let me switch gear. That's enough about the three parameters. Well, I know we have time limit for today's talk. So another great facility we have had in the College of Ag is the Indiana Corn and Soybean Innovation Center. This center was 2 years ahead of AAPF. Actually, it was built in the year 2016. ICSC is a fully integrated field facility that accommodates plant and seed analysis with proximal, near proximal, or remote sensing for that matter, that support a wide variety of research, including phenotyping research. I also have the virtual tour link here at the bottom. So if you're interested, you're more than welcome to visit us virtually, or if you have time, you're welcome to visit in person as well. If or when you come to the facility, either virtually or in person, you'll see that ICSC is a facility at the footage over 25,000 square foot. This big building accommodates an array of state-of-the-art technologies to accommodate that enables research in plant and seed processing, extraction and shelling, seed analysis and storage, as well as we have space, actually multiple space, to accommodate sensor development or system development at the center. We also have high-speed fiber optic data conduit just to enable data transfer from the center over back to the main campus. The center also possesses a set of shared instruments that can be checked out by different PIs for their purpose. For example, we have LiDAR 6400 as well as a LiDAR 6800 for photosynthesis measurement. We have LiDAR 2200 for e-variable index modification, and a root washing station and other instruments. In here, you can see there's a bunch of students, researchers doing plant management and processing in the open space, common space there. We have this shelling and extraction systems in its dedicated space. ICSC has not only served as a base for PIs to carry out research. Ever since its commissioning of this building, it's also served as a hub for multidisciplinary interaction and collaboration. The professors from College of Agriculture, from engineering, and from data science all come to the common space to carry their research, even though from different angles, but for the same topic in plant science, in plant science. So those great collaboration has created a lot of know-how and expertise in remote sensing, in data processing. So in order to reap those achievements and provide the service to benefit more researchers across campus, we started to provide UAV-based plant sensing service to anyone on campus, acre or at other sites. The service was started in the year 2020. Initially, we have RGB and multispectral imaging capabilities provided for the year 2020. And then in 2021, we upgrade our platform with a combination of RGB, LiDAR, and a visible to near-infrared hyperspectral imaging. We are now working on expanding our fleet because we do have strong needs, strong demand of research demand, acre and other sites. And we're also expanding our sensing capabilities for the UAV systems. Right now, we're working on adding a sphere camera, and eventually, we're also working on the capability to provide a thermal imaging service to customers across campus. On this page, the stitched image or the mosaic image is the example of the color image we are able to provide as a critical deliverable to our customers. Also, we can help you to create the grid to separate the plots, just so we can extract information from at the plot level. If you have capability to go from there, you are welcome to use the data. If you need help, need consultation to say, hey, how do we go further in terms of analyzing the data? We do have embedded expertise at the plant science team to help you go through the process in terms of leveraging this type of data to carry on the spatial as well as temporal management using this type of information. We also leveraged heavily the Griffin software package to process the hyperspectral data, which goes from the stitching the image together to establish a mask that helps us to identify the target in the field. I'm going to share with you a short movie that consists of a series of vegetation indices that can be constructed using the linear camera. This is the same field, but for the same field, we can, because we have different ways of creating different VIs, then there's a different angle, different way for us to quantify and also visualize the same field in different ways to quickly help us identify if there's any issues across the field. The third part of the pipeline that we are able to now, at this point in time, provide to our customer is the LiDAR system. LiDAR is the short for light detection and ranging. The pipeline provides, again, on the screen, this is an example, 3D point clouds of the field. And from there, we can, of course, help our customer to use this data to make comparison and quantification of quite a few different things. For example, here is the height of our plants. In this example, it happens to be that the inbred plants were grown right next to the hybrids. We can clearly see the difference in terms of the height using the LiDAR data here. Of course, again, this is just a way of visualizing the data. Dr. Tynstra's lab has since leveraged this type of data to calculate or to measure the height of the plants at the plot level across the research field. So this then serves as a very efficient, high throughput way of measuring the plant height across the research research field, instead of any one of us taking a stick into the field to measure the tens of hundreds of plants across the research domain. Now, let me switch gear again to quickly touch on what to expect in the next couple of years. So because of the achievement in the plant science 1.0, we now have the opportunity to further enhance what we have achieved in the PURDUE'S move, which is for us established the plant science 2.0. The general objective is to leverage the advance in phenotyping and the digital agriculture from the plant science 1.0 and to add value to plants and forest products by optimizing plant productivity, nutrition, and accessibility traits. Again, it's a mouthful to even read them. But suffice to say, we are seeing another big opportunity building on what we have achieved to push the plant sensing, the plant science further into a different domain and at a enhanced capabilities. Speaking of facility that we're going to look or see in the next couple of years, one of them is the new greenhouse. In this computer rendered image, this building is the AAPF that I just kind of lead you through a VIP type of tour. This is the new greenhouse that's currently in engineering phase. Hopefully, in a couple of years, if we have a chance to meet together, I may be able to tell you, hey, this greenhouse is ready for you to visit or for the scientists to take advantage to carry the research in. Another facility that's been in discussion and has been in designing phase is the rainout shelter at Acre. A rainout shelter actually, most strictly speaking, is more of a managed irrigation management type of facility in which we can precisely manage the watering regime, no matter the rain, the snow, or the no rain, no snow here at Indiana, just so we can create a different water regime even in the environment here. So that can enable a lot of different type of research in the field. The engineering design for this facility is more or less wrapped up, finished and wrapped up. We're looking for opportunity for investment, just so to make it happen. With that slide, I wrap up my talk today. I'm open to any questions or comments. Thank you.
Okay, who has questions? I have one if no one else does.
Okay.
Can you monitor or what's in the chat? Anything in the chat?
Nothing on the chat yet.
Okay, so I do have a question for you, Yang. How much is this technology being used by commercial plant breeders at companies like at Corteva and Bayer, and we all know the big plant breeding companies? And so is it used commercially? Is this more in the research phase right now?
Actually, as a matter of fact, the industry was ahead of academia in terms of building the phenotyping facilities. Corteva actually has a very large indoor phenotyping facility in Iowa, Johnston. In a similar way as what we have in AAPF, it's more like greenhouse based, but the sensing capability and the scale are more or less similar to us. Monsanto, now they call themselves Bayer, also has had a significant investment in this domain until a few years ago. They have a change of heart. Other bigger players like Syngenta, that's nowadays it's called one of the big threes, right? The Bayer, the Corteva, the Syngenta. Two of these big threes do have their own capabilities and expertise in phenotyping. Monsanto, I said they have a change of heart is because they gave up their indoor facility. However, they do have very strong expertise in plant remote sensing and plant management in the field. Yes.
So I know you and I have a separate conversation about this one, but I bet all these facilities will generate a lot of data. How you are managing those data right now, and how you are sharing these data with all the scientists, or do you have any kind of vision for how to improve those data management?
Good question. Good question. I'm not sure if online can hear the question. Let me repeat first. So Dr. Jin's question is, this type of sensing capabilities in either the indoor and or infield capability phenotyping facility, because of the characteristic of the sensors, we're able to create or accumulate a very large amount of data, very large volume of data. How do we see that's the appropriate way of managing the data? How do we share information just so that the users or the PIs can use the information rather than dig into the raw? That's a perfect question. The short answer is that we can do better. The longer version is that there's so many different ways that we can look into a database type of system that can help us to manage, to query, and to process either the raw data or the curated ones. We're on the way. We can use the help, like experts like you guys, to help us do a better job in processing the data, in managing the data as well. But thank you for the question. It's very important.
I didn't realize you had such capabilities for root imaging. And I think that's fantastic because I know that's that underworld that that's always been mysterious, that we've always needed more data about. And I'm curious, do you have to have a certain potting medium for that? And would you just briefly describe what that is? Is it sand? Is it all organic, or how does that work?
Great question.
Okay.
So far in the facility we use what we call the off-the-shelf horticulture mix. It's more of a peat plus some bark type of mixture.
Those big piles of stuff back in that greenhouse service building? Yeah.
There are some limitations, I'll be honest, because the size of the box, if they are so close to the root in terms of diameter, then you'll confuse the software. Well, again, that's the part we can use engineers help to help us do a better job, just so we are not limited as much by type of pot media. There are publications in which other groups have used sand as or even soil.
I mean, I know back in the olden days, you used sand because it would remove itself from the roots very easily. Yeah, fall away.
Right. Yeah. For X-ray axis is the other reason. It's relatively.
I mean, that's when you took the medium away from the roots, and now you leave it all together, right?
Yes.
Right.
Yeah. But according to Fraunhofer Group, which actually is a vendor that's the machine to us, it's relatively easier if the media is falls into certain categories, and sand is one of the ones that provides some easier time when we try to segment out roots away from pot.
Okay, other question. I have to leave for another meeting.
Yeah, thanks.
The plant will show any difference from the plant growing up on the conveyor will show any difference from those growing up on the ground.
Oh yeah. The question is if when the plant grows on a conveyor belt and in the pod, is that different? Do we see difference from the ones that grow in the ground, right? Yeah, of course there are. They're never the same. You cannot explain the same because it's pod versus the real soil. They're never the same. But in that sense, we have to always keep in mind that when we can try to make the connection between the control environment data to the ones that we collect from the field, it's never going to be one-to-one, right? There's need to be a what we call transfer learning between those two facilities. Yes.
For the root scanning, does moisture matter?
Does moisture matter in the root scanning process? Yes. For X-ray CT, for X-ray itself, actually, if the soil moisture is too high, it's not a scientific answer. But if it's too high, then the sensor will have a harder time seeing the root. So we need to reduce the soil moisture to a certain level, just so the energy has enough. The sensor has enough energy to penetrate basically the whole target.
Then the next question is that for the scanning, about 100 micron.
That's the resolution. Yes, yeah.
Does put in perspective, does that can evenly detect fine roots or root hairs, or what the level there, or microbial?
Okay.
Interface, like what level?
Yeah, what level? Basically, finer than our hair, we can see. However, if it's what we did at this point of time, successfully scanned the roots in the way of corn, tomato, soybean, and those trees I just showed on the screen. But we are still trying to figure out a way to scan the root for other crops, such as especially like in wheat, when the root is much finer. That's when we are still trying to figure out if or when in which way we can make the sensor see see the root. There's a lot of factors plays into the capability in terms of the resolution. The software package itself is one, and then the sensor, of course, physically that's the limitation, and also the volume of the root. The bigger the volume, the harder it is for us to find the finer root. But there's a lot of factors that we are still working out. Actually, if we're sitting here, I expect him to join us in the near future to work on this as well.
Baishan, Yang have a question.
Yes. Thank you, Dr. Young. That's a great services you're providing to the community. I'm really interested in the UAV services you are providing. In particular, one thing we discovered was the whatever the images you RGB image you got between different flights have a lot of variation because the height, the different camera, and all that really impact how we're going to using deep learning, try to do further analysis or research. So my question to you are two of them. One, do you have any way to kind of reduce that kind of variation when you fly UAV to capture that image? The second question is, I think you also mentioned you can do LiDAR. So when you do the LiDAR, do you actually fly them together, like RGB and LiDAR together, or separate? Thank you.
The second one is easier for me to answer. We do it together. We fly the sensors as a combo.
Okay, good.
Yeah. In terms of figuring out what's a better protocol to minimize the noise in the data set, at this point of time, my team, we have not worked on that. So far, our mode of action is that we provide data. We haven't really had a chance to work with any professors to dig deeper into in terms of how we can provide better data in that sense. So if you're interested, we can have more discussions with you to see if we can provide you more data for that purpose.
Thank you. Appreciate it.
Sure.
Probably I can chime in here a little bit because I'm from geomatics. That's what we do.
Yeah.
So RGB camera that they flying, it's not I'm going to say that the scientific senses. It's more for visualization. The weather condition is going to be a big factor to see how those RGBs look like. But the hyperspectral sensor, we do have ready-made calibration procedures so that it's going to be much less prone to variation depending on what kind of weather the condition it is during the collection. So if you're looking for a more consistent data set, you need to stick with the sensors that they can have ready-made calibration capabilities that can be hyperspectral and the multispectral with the solar sensor attached to it. RGB is not meant to be calibrated. It's more for visual and structural analysis.
Right. Great comment. Can online people hear Dr. Jinha's comment?
It was a little faint.
If not, I'll try to paraphrase. So in the world of UAV-based remote sensing, the RGB data in essence is not fully calibrated. There's a lot of noise or a lot source of noise in the sense of radiation as well as geometry. On the other side, if or when we are flying a sensor such as hyperspectral, then hyperspectral sensor imager, then we have a protocol established to take into account the change in radiation conditions. So in other words, when we have appropriate environment condition, if we know and we go follow the calibration procedure more closely, then you have a better chance of having a more consistent data set when you run hyper versus when you run RGB. Is that okay? Yep. Thank you.
Okay, any other questions? I'm happy finishing off. Bruce after me. Any more questions online? Okay, if not, let's give another round of applause to next week. We have another seminar that is about using remote sensing for agriculture and natural resources. We have a person a professor from the University of Minnesota. And some of them are gonna be in person.
Okay. It's gonna be not Zoom, but in person?
Yeah, because the person is visiting us.
Oh, okay, got it.
And I think we might be able to have some freedom stuff as well.
Are we also gonna do hybrid?
Yeah. We will be. So, all right, well, thanks, everyone.